absolutely. Yeah. So it will be by Paul Bachek. I hope I'm not butchering the name. Electrical engineer from the Brookhaven National Laboratory. And he's going to talk to us about clock recovery from high-speed links. Just let's see another approach, another method.
Test. You me? How about now? Yeah. Okay. Thanks.
Okay, thank you.
Okay, good afternoon, everybody. I'm going to talk about deterministic frame clock recovery in Ultrascale plus transceivers. And this will be used in the timing system for the Electron Ion Collider, or the EIC, which is currently under development at Brookhaven. And so just some background about the facility. Brookhaven National Lab is based in the United States and currently operate a heavy ion collider. And the Electron Ion Collider is an upgrade to the heavy ion collider to add an electron ring to support electron-hadron collisions. And so this is one of the, some of the ongoing work with the timing system for the EIC, Electron Ion Collider. So the timing data link is a custom network protocol that we're going to be using for the EIC timing system. The two key parts are it distributes the 100 megahertz accelerator master clock to all of the timing endpoints, along with timing and machine and debug information. So the basic structure of the data packets transmitted over the link, it's 64-bit packets, and you get one packet every cycle of the 100 megahertz master clock. The diagram on the right shows a simple timing diagram to show how packets are transmitted. And we use AP10B encoding with each byte in the 64-bit packet. So this yields 80 bits total per packet. And so the final line rate, 80 bits at 100 megahertz, we get 8 gigabits per second going out on the line. And we're using Xilinx Ultrascale Transceivers with SFP modules to transmit using fiber optics. So one of the more difficult tasks is deterministically transmitting and recovering the 100 megahertz accelerator master clock using the serialized data from a transceiver. The transmitter has to serialize the data so that the first transmitted bit coincides with the rising edge of the master clock, and then the job of the receiver is to deserialize the data and extract the recovered clock in a phase deterministic manner, which can be done, but it requires some careful configuration of the transceiver to make sure that the phase of the recovered clock is deterministic across resets and bringing up and losing a link and reconnecting. So first I'll go over how the transmitter serializes the data. The important thing to see here in this diagram, which shows the clocking structure inside of the GTH transceiver in the ultrascale, is the parallel in, serial out data register. Parallel data is clocked in using the clock highlighted in red, and it's clocked out at the line rate when it's serialized to be transmitted. So the user cannot directly drive the clock that's highlighted in red here to control how the data is framed and transmitted. Instead, there's an IP core, the PIXO, that controls the phase interpolator just below the register in the diagram there to finely tune the phase of the transmitter parallel clock in order to control the data framing that gets transmitted on the line. So we will use this in addition to our accelerator master clock to make sure that they're phase aligned so that the data always comes out aligned with our clock. And so our accelerator master clock in this picture is highlighted in green. We feed it into the channel through the MGT ref clock. and then it can be forwarded to fabric through the long green clock path shown at the bottom. So that is sent into fabric to the PIXO IP, and that's used to align the TX out clock, which in turn aligns the PISO clock, and then the transmitted data is aligned the way we want it. So just a little bit about the PIXO IP core. They give you a nice calculator, Excel spreadsheet-based tool to make sure that the gains for the PI loop are stable. It can change based upon the configuration of the GT, but this tool lets you know that it'll lock within a reasonable amount of time and be stable. So a little bit more tricky is the receiver recovering the clock. The serial in, parallel out register shown in the clocking diagram here, which looks a lot like the transmitter diagram, but the data's coming in instead of going out. It's the receiver end. The parallel clock, which is the clock path in red in the diagram, controls how data is deserialized out of the receive serial register and then presented eventually to the user logic. Again, the FPGA fabric cannot directly drive this clock. It's generated from the phase interpolator, which locks to the incoming data line rate and then generates a divided down clock internally to the transceiver. The recovered clock, which comes to fabric, RX out clock, can be routed through fabric and then output, which is phase aligned to the incoming data using buffer bypass mode, but with a few notable problems. One of them is that across resets, this delay aligner, which is shown in the clock path right before the RX clock goes out to the fabric, it introduces nonlinearities and inconsistencies across reset with the clock phase. So what you see is the clock will come out and you're locked to the data and it looks like it's in phase, and then the transceiver resets and it can jump by orders of tens of picoseconds or sometimes more depending upon temperature variations. So ideally we want it to be exactly repeatable and stable across resets and losing and re-establishing the link. So that's the biggest problem with doing it this way. Fortunately, there's another clock, this RX recovered clock, which gets output directly within the transceiver quad to the MGT ref clock pins. It has dedicated routing. It doesn't pass through any of the fabric logic at all. It doesn't go through the delay aligner. It just comes straight out through dedicated I/O. And so this is ideal. We can output our recovered clock, and it'll be exactly repeatable across resets. And the only problem is it has no phase relationship with the deserializer parallel clock, which is in red in this diagram. They're generated by completely independent dividers, which come up at different values after a reset. So they're synchronous with each other, but the phase is not predictable. So what we have to do is manually align these two clocks so that we can have this clock output deterministic in phase clock with the received data. So this is just some more motivation for using the recovered clock output instead of the one that goes through fabric. This graph shows the jitter performance in blue of the recovered clock that goes directly out. And you can see it's much better than the one in red, which is the clock that goes through fabric. And this is not my graph. This was measurements taken here at CERN and published in this paper credited here. It just shows some motivation for the improved jitter performance of the recovered clock. So how do we align the RX recovered clock? The first step is to enable buffer bypass mode, as was done in the previous method, but this time with the recovered clock sourcing the RX out clock, and that whole path is shown in green. You can see it. I hope the color comes out. And the auto alignment feature, which uses the delay aligner, is used to make sure that the deserializer clock is in phase with the recovered clock in green, and you can see the auto alignment gets the red deserializer clock and what they call X clock in the green path on the right, make sure that they're aligned. And the problem is that we're aligning this clock to a version of the recovered clock that is still delayed through fabric and whatever clock resources, including a PLL in this case. So we're still going to see phase variations, and also we can't use the RX slide feature to align our data to a comma boundary, because if we do that, then we'll shift these two clocks out of alignment, which was the original goal. So how do we overcome these two problems? We can start by measuring the skew of the path from the clock out of the transceiver through fabric and back to X clock, where it's measured for the clock domain crossing. And this can be done by changing the RX out clock source to be the deserializer clock, and then use that to measure its phase back through its entire routing path back to itself. And then the delay is accounted for entirely in the delay aligner block, which can be read out to fabric, and that value can be saved. And this represents the entire path delay that we are trying to compensate for here. And this can be done using these special transceiver configurations. And the delay aligner is just basically a 256 tap delay chain, which is used to align the X clock and the deserializer clock to make sure you have a valid clock domain crossing in the receive path. So this measured delay value is not much use to us by itself, but we can use it to find the phase difference between the SIPO parallel clock, the deserializer clock, and the recovered clock in green. So we can notice that they're both generated by the CDR clock that comes out of the phase interpolator, and then we know, therefore, that they have to only differ by an integer number of that higher clock frequency periods. So we can measure this period, how many clock periods they differ by exactly, by changing the RX out clock source back to the programmable divider clock, the recovered clock, and then manually shifting the SIPO clock until the delay aligner value matches the one that was just read. And once they match, we count the number of shifts we had to perform. And that number of shifts is exactly the number of CDR clock periods that they differ in phase by. So this is useful information, because if we know the difference in phase between our deserializer clock and the recovered clock that gets sent out, we can compensate for that by shifting the data here. So we can't just go and shift the deserializer clock to whatever we want it to be, because it was aligned by the auto alignment procedure in order to create a valid clock domain crossing. So we can't mess with that, or else we'll start to see data errors. So we have to make sure that the clocks were aligned as they were originally by the auto alignment algorithm, and then we can shift the data that's presented to the user logic by the same number of bits as we found in the previous step, and that will allow us to have data presented to the user logic as if the recovered clock that we're sending out is actually deserializing the data, so that they're always in phase. And this is all good, but the only problem is we have not aligned the data to a comma boundary yet. So in order to do that, we can't shift the deserializer clock, because it has to be in line with the recovered clock out in order for the valid clock domain crossing. But what we can do is manually shift the clock that generates both of them that comes out of the CDR. And that can be done by manually controlling the phase interpolator. And this is demonstrated in this app note from Xilinx, which is meant to enable the transceiver to lock to pulsed optical networks, but the same principle applies. They read and control the phase interpolator in the CDR. So what we want to do here is control the taps in the phase interpolator in such a way that we can effectively skip 1 bit in the received data. This way, we can shift the CDR clock an arbitrary number of bits in order to align to a comma boundary, and also shift the recovered clock and the deserializer clock exactly the same number, by the same phase, because they're generated from the CDR clock. So to do this, it requires some special configuration, and the idea is you just cycle the phase interpolator through every tap value until it rolls over, and keep going until the original value that it was at, and then effectively that shifts it by 1 unit interval bit period. So now we can do a bit slip from the user logic. So this is all we need, and now the user logic can use the comma detect features in the transceiver without any extra analysis on the received data to align to the data and have the recovered clock come out of the transceiver without any phase variations and always locked to the first received bit on the received data. So just a quick summary of what we did. We aligned the recovered clock that comes out of the transceiver and not routed through fabric using the buffer bypass auto alignment feature. We compensated for the fabric delays, which would affect the alignment of the deserializer clock and the recovered clock. And then we aligned the data to a comma boundary, in turn shifting the recovered clock onto exactly where we want it in phase with the recovered data. So now the job of the receiver is done. We have recovered the frame clock of the data, and it's deterministic. It doesn't vary across resets, and it's much more stable over temperature than a clock that wraps through fabric and through this delay aligner. So there are a few potential complications depending upon how the transceiver is configured, and some of them are listed out here, but there's ways to overcome them just by slightly changing the algorithm. And so this was tested on a Xilinx Ultrascale eval board using this configuration that we're going to use for the timing data link for the EIC. It's 64-bit words. One thing with the GTH transceiver is it only has a 40-bit internal data path, so we have to use a different RX user clock 2 frequency in order to get 2 40-bit words per 64-bit word on our line, but this algorithm was implemented successfully, and we were able to measure no clock skew variations across many reset cycles, and this oscilloscope could only measure down to 1 picosecond variation, but that was enough for us. It's just verifying that the algorithm works and it's repeatable over temperature. And that's it. So any questions?
Thank you very much, Paul. Questions, please? Oops. Yes. No mics there, right? Yeah, maybe try this one.
Hi, we make a protocol similar to this that distribute the clock. My question is related to the transmitter that you say that is the easy part. I agree.
Just a little bit more.
Yeah, it's the transmitter is the easy part, but the problem is that the QPLL, every time you reboot the board, assume a random phase, what I see. The QPLL.
What about the QPLL?
The PLL of the transceiver.
What about it?
It has a random phase in respect of the input clock. I think you fixed this problem because you said that you measured the phase relationship, but it was not clear to me how you did it.
I'll go back to the Xilinx clocking diagram. So the QPLL clock, you're saying, is not in phase with what clock?
With the clock, the MGT reference clock.
Well, so it's generated from the MGT reference clock.
Yes,
so it's synchronous, and it's usually at a much higher frequency. So like, for example, in our case, the MGT reference clock is 100 megahertz. That's our accelerator master clock. Generates the QPLL clock, which is at our line rate of 8 gigahertz, and they're synchronous. And so it's divided back down after the phase interpolator through the divider paths, again to be 100 megahertz, but the original MGT ref clock, 100 megahertz, is not in phase with the re-divided down version of it. They differ by some integer number of the 8 gigahertz clock. So the job of this algorithm is to measure how many 8 gigahertz clock periods they differ by, because it's multiplied up and divided back down.
Okay, but at the end you will get a clock on the receiver that is synchronous with the clock that you provide to the reference clock, or not?
So this is on the receiver. So the MGT reference clock on the receiver does not. It's just a local, no reference to the global accelerator clock. Our job is to recover the accelerator clock, which is encoded in the received data.
Okay.
So the MGT ref clock in this case of the receiver, there's one input, which is a local 100 megahertz oscillator with no phase relationship to anything. And then the other MGT ref for that quad will be an output, which is the recovered clock.
Because we have 256 receiver that are all that are all synchronized with a jitter of 10 picoseconds, but they are not synchronized. They are jitter in respect of the MGT clock. Jitter not in the meaning that you see that they are jittering, but if you switch off the system and you power on the system again, you are getting that the phase between all the 256 receivers that are all locked in phase, it's not constant in respect of the MGT clock. And I just want to know if you solved this problem in some way.
I don't fully understand. Maybe we can talk.
Maybe I will explain because it's more complex. Maybe I will make a diagram. Okay, thank you.
Thank you.
All right, anybody else? Nikita, please.
Hi. So in your approach, you are using the RX rec clock out as a reference, right? This is your reference to align the SIPO parallel clock.
Right, here, I'll go to the other diagram. It's a little more clear. So yeah, the recovered clock out, which they call programmable divider clock,
Right.
is driven to RX out clock, back into the transceiver as user clock, and then that eventually goes to X clock, which is used for the alignment.
So could you use the RX, you have it there, the green arrow, could you use it directly as your recovered clock so that which goes out of the FPGA without passing through the fabric?
That's what we do. Yeah, so there's two arrows. The one that goes to the left goes out of the FPGA, and that's actually used in the system to go to the jitter cleaner to be distributed for use.
And a second question is this system, and did you take into account temperature variations?
Yeah, so I did two things for testing. I don't have good data on it, but just in the lab, I tested over, roughly 40-degree temperature swing. But I think more importantly, I added variable delay phase shift to the PLL, which is in the diagram in the bottom right here. So I phase shifted the clock that goes through fabric through an entire cycle. And then I saw the recovered clock that comes out of the chip that I'm interested in does not vary at all.
All right.
Which basically means the fabric delay variations have no effect on the recovered clock.
So we have a similar approach. I'm happy to see this clock being stable in your test, the RX rec clock out. Okay, thank you.
Anybody else? I don't see anybody. Let me then ask a question. So I guess many people are looking for a solution. Are you going to share your algorithm? There may possibly many clients about that method. Are you going to share the code or something that people could?
I'm working on making the code public. I'm working on making the code public.
All right, that would be very interesting, I guess.
Yet, but it will be.
But from what I understand, the systems need a specific hardware feature to do it, right? So they need to output the rec clock, so they have to have it in their hardware should support it, right?
Fortunately, this only uses FPGA resources, so it doesn't need any ancillary components.
No, but what I'm saying is that you have to have a way to output the rec clock, right?
This clock has to be connected on the board. And
all right,
routed typically back into another reference clock in the transceiver.
Yeah. All right. Okay, then maybe it's a good time to break for coffee. The sessions will continue at 4:30. Again, with the second part of solutions to everyday digital problems. So see you at 4:30. Thank you.